This was supposed to be the final video in the series, but it got so long that I'm splitting it into two parts. Let's start part 3 with the quiz. And the answer is the answer depends on which datum you're using. For maps, that word means two things. A datum can be a physical marker, such as this one in New Mexico. It can also be an abstract system for determining three-dimensional coordinates based on our understanding of the Earth's shape. To explain what datums do and why hikers should care, I need to go into a fair amount of history. In the old days, celestial observations plus chronometers gave people their longitude and latitude, but there was always some error. Being hundreds of meters off wasn't a big deal if you were on a ship crossing an ocean, because once you saw land, you switched to other navigational aids. At least in principle. If you were hundreds of meters off and struck a reef, it was a big deal. But this video is for hikers, so let's talk about what happened on land. If you were a land surveyor in the old days, you couldn't get the accuracy you needed by independently measuring points the way it was done at sea. You needed something else. That something else was triangulation, and here's how it worked. You created a single physical point called a datum. Then you established a second point, also called a datum. You very carefully measured the distance and bearing to that second point. Usually that involves stretching a special chain across the ground again and again until you measured how many chains it was between your 2 points. Next, you determined the exact location of a third point relative to those first 2 points. The good news was you didn't have to measure the distances to the third point using that annoying chain. Instead, you used math to figure out where the third point was. From there, it was just a matter of establishing new datums and establishing their locations relative to the existing datums using the same math. Once you had enough datums, you could measure off them to fill in the rest of your map. Triangulation gives you elevations as well as horizontal positions. Here's the original triangulation system for Switzerland. But there's a problem. All of these points are relative to each other, but so far you don't know where these points are relative to the entire planet. In other words, all of these points are floating in space. To fix the problem, surveyors defined a master reference point for each triangulation grid, also called a datum, of course. The arrow shows the location of the 1903 master datum for Switzerland at an old observatory in Bern. Once the Swiss established that master reference point, they very carefully estimated its longitude and latitude. And once they had the estimate, they could use math to calculate the long lat values for other physical datums in the system. But in the end, the location of the Swiss master datum was still just an estimate. In part, the inaccuracy was caused by the shape of the Earth, which isn't a true sphere. From time to time, people came up with better and better guesses about the actual relationship between their regional triangulation system and the planet. When they did, they established new regional datums. I'll use North America as my example, but the problem of changing datums applies to other land masses as well. In the contiguous United States, a new datum established in 1927 became the master reference system for the next 56 years. This datum, in the abstract sense, included a datum in the physical sense in a pasture in Kansas. Why Kansas, you ask? Because it's more or less in the center of North America. The guess as to where this datum was relative to the planet got carried through to the rest of the triangulation grid. When UTMs first came along in North America, that grid was also positioned relative to the physical datum in Kansas. Eventually, thanks to satellites, people came up with much more accurate estimates of where they were. All over the world, old datums were replaced by new ones. In the United States, we got NAD 83. This 1989 map was printed during the transition from the old system to the new one. The map is telling you that it was prepared using NAD 27 and that the UTM grid is tied to that datum. The upper arrow shows one of the ticks for the UTM grid. The map is also telling you that if you use NAD 83, the corner of that map should actually be where the upper arrow indicates. So where is the physical master datum for NAD 83, you ask? Actually, NAD 83 doesn't have a constructed reference point the way NAD 27 did. Instead, the starting point for NAD 83 is the center of the Earth. In case this isn't confusing enough, right after NAD 83 became the new master system for North America, we got WGS 84. This is a big deal, actually. Before WGS 84, the answer to the initial quiz was no. In fact, the North American datum was a floating system. Ever since WGS 84 was adopted, coordinate values in the United States have been tied to a single international standard. So, starting in the 1980s, the answer to the quiz became yes. If you lasted this long, you're about to find out why a hiker should care. Suppose you pull coordinates for a point off Google Earth and load those coordinates into your GPS. You're counting on your GPS to take you right to that point. Google Earth coordinates are based on WGS 84, and let's say your GPS is set to NAD 83. Should you worry? For a hiker, the answer is no. NAD 83 and WGS 84 aren't identical, but on a hike, you'll never notice the difference. But let's say you pull coordinates off Google Earth and your GPS is set to NAD 27. Should you worry? This time the answer is yes. The GPS is going to store the Google Earth number values on the assumption that they're relative to NAD 27. Under extreme conditions, the difference between where you think you are and where you actually are can kill you. So before you upload any coordinates from Google Earth or from any other source, make sure your GPS is set to the same datum your source is using. Before we quit part 3, let's look at a map I use all the time. Because you slogged through these first 3 videos, the legend is going to make a lot more sense than it would have before. For starters, you can see that the map is based on NAD 83, so that's the datum your GPS should be set to. But, as I mentioned, if you set it to WGS 84, the error will be so small that you won't notice it during a hike. Usually the difference between the two is about 1 meter. This map is in UTM Zone 13, but it doesn't specify which hemisphere or horizontal band. That's a bit sloppy, but we're talking New Mexico, so you can guess that it's the Zone 13 grid for the Northern Hemisphere. Those are UTM easting values along the top of the map. The UTM grid marks are hard to see, so I marked one with the lower arrow. There are also longitude and latitude values. The hiking guide this map came with uses degrees and decimal minutes, so it's nice to have long lat tick marks on the map. Finally, what's this? It's a statement that the elevations on this map are based on an estimate of sea level made in 1929. That estimate is obsolete, but it's off by less than 2 meters, so as a hiker, you'll never notice. I'm throwing this in to remind you that you can't learn every possible aspect of coordinate systems in a few short videos. Still, if you absorb the information in this video series, you'll have a better understanding of coordinate systems than at least 90% of hikers. As I said, I have a bit more material to cover, so eventually there will be a 4th video in this series. Meanwhile, thanks for watching, and I hope you learned something useful.